Thank you. Thanks for having us on. And I'd really like to thank the Dominguez Rancho Adobe Museum for basically hosting our webinar of the whole Wild California series. I'd also really like to thank the California Naturalist Program and Elliot in particular for assisting in making this possible. I would also like to say, before we get underway today, even though we are not getting to meet on the museum grounds at this time because of necessary measures, a certain situation applies no matter where we are. And in that light, we would really like to acknowledge that the land on which we are gathered here today, wherever we are, is the home and traditional land belonging to the Tongvan Nation. If you're joining us from elsewhere, then your local tribe, to their nation. Today we come with respect and gratitude for the Tongva people who still consider themselves the caretakers of this land. It is through their examples that we are reminded of our greater responsibility to take care of Mother Earth and to take care of each other. In that light and in that spirit, let's go ahead and let's talk about some necessary, interesting and difficult and long-running conversations that we need to have about not just California, but our greater planet at large. So welcome to Wild California. Today, we're going to be talking about climate change, not just what it is, but what it happens, how we perceive it, how can you measure it, how can we understand what's going on, and hopefully, what can we do about it? It frequently is not really useful, especially when you have a difficult subject, to just talk about what is wrong with a situation. But it is necessary to talk about what is true about a situation and what the history and the, as accurate as we can make, predictions for a situation are, so that when we try and talk about potential solutions or whatever measures we can take to try and moderate a situation, that those conversations about what we can do are then as useful and as accurate and hopefully as successful as possible. So we're going to talk a little bit about what climate change is, and then we're going to get into how it has happened in the past and what is different about that now. Global climate change has also historically been called global warming, and this sometimes can be a bit of a misnomer. It is true, the overall temperature of the planet has been rising, but that affects different areas in different ways, and the reason for that is it's going to change the weather that comes into an area in different ways. See, weather has to do with what weather patterns, sun versus cloud versus what kind of precipitation, whether that precipitation falls into an area as rain or sleet or snow. Climate helps determine what form that precipitation is going to take, how long that water is going to hang around once it falls. Is it falling in Washington State and stands a better chance of actually staying for a little while, or is it going to fall in Southern California and evaporate very quickly because it's otherwise so hot and dry? So weather is basically the fact of what is it like outside. Climate is the consequence of what it's like outside and how that starts to affect a living system. Weather is temperature and amount of rain. Climate is all of that, plus what kind of habitat that starts to create as that has its effect over time. So we're going to be looking at some of both of these effects as we're discussing climate change and global warming this morning. Global climate change is measured and studied in three major ways. How it has happened both currently and in the past. And this is something that's really interesting to talk about, because when we start looking at, well, what's causing climate change, one of the best ways we can try and figure this out scientifically is by looking and comparing at both historical climate change patterns. And yes, we have historical climate change patterns as far back as we can find records for, whether those are human kept records or records we have the ability to perceive and measure in nature. And by comparing these and by comparing what was going on at the time, we can try and establish the next major area of study, which is Why? What happened? What are the causes for climate change? How did climate change happen historically? Maybe even in prehistoric Earth. But also ongoing climate change during human history, which is something we don't really talk about very often, do we? We don't talk about mostly pre-industrial era climate change, although there were some instances of it. Uh, and we talk about how is that different now versus what's going on in more comparatively recent history that's created much more severe, much faster acting phenomenon. And of course, especially for folks wanting to discuss what's going on right now, one of the most important, one of sometimes the most worrisome or dramatic areas of study is what are those results? What's happening because of climate change, or what has happened because of climate change? So let's try and understand what is the history on this planet of this subject as much as we can, so we can better understand what's going on going forward. What happens to cause it? What's going on? How do we recognize the signs when it's going to happen? Certain effects coming back into activity? And how do we understand what is happening because of climate change versus something else? And how do we predict what's going to happen further on in the future, both globally and even in our local area? Records of climate change, and this is particularly looking at historical evidence of global climate change, have to, by necessity, go far past what we have recorded as human beings. Climate change is usually, and that's a really important operative word right now, climate change is usually a slow, gradual process. Slow enough and taking long enough and starting at old enough periods of time that non-recorded, this is going to sound counterintuitive, non-recorded records, signs of climate change that were not written down by people, that were not observed directly at the time by human beings, can frequently be the best for us to start studying how climate has changed over time, over Earth's history. Now, when we're talking about really long periods of global climate change, there are sometimes great difficulty. There is sometimes great difficulty in finding decent records. If you're looking at something more recent, yes, you may have human records, but you know, what are the quality of those? Have they suffered? Have they been lost? Have physical pieces of those records been damaged or been lost over time? You also have to work with what was the level of scientific understanding of the people living through that time. We also, and this is sometimes both hilarious and frustrating, and you know what, sometimes quite humbling. We sometimes run into areas, even in records that have been kept by humans, by people in their society, as they just observe what's going on with their climate over time, where aspects of information that as scientists, especially dealing with climate change right now, we would find to be really crucial information. Sometimes those aspects, those observations, were considered to be so commonplace or unimportant that they just were not noted. They sometimes get referenced in historical records. Sometimes they are the records of monks or landholders or church record keepers for their various towns. For example, these are really common areas where we can still find even early kept records. But they'll notice something sort of tangentially in passing, and any climatologist looking through these records suddenly goes, no, go back to that. No, go talk about that again. But for the people living through that time period, it was just how things were, and they don't necessarily make really clear discussion or a really clear note of what was going on, even though in hindsight, we're like, oh God, that would have been really useful. That would have been exactly the kind of information we were looking for. There is quite a bit of sort of various scientific heads banging on desks sometimes when we are looking at past records. Sometimes looking through that sort of record isn't even an option. Either because we're looking through an area where records were not kept just because of the culture at the time, or they've been lost, or we're looking at a time period before, long before, human records were evolutionarily even possible. And that's when we start looking at indirect evidence of climate change. This is time when sometimes a really good geologist is a climatologist's best friend. There are certain signs of climate change, side effects of climate change, that are actually laid down in the geological record. They're right down there with the fossil record. One of the classic signs is the increase of oxygen in our Earth's climate. And every time this has happened, we can see it laid down as a rust-colored layer, actual rust. It's actually the exact same chemical reaction, oxidation, that happens with metal left out, well, in some place over the winter, not Southern California. But we can see this indirect evidence actually laid down in the layers of rock down underground. There are other forms of gas that lay down their own records in the geological record. Now, oxygen is easy. It lays down a nice distinctive red rust-colored band. Other signs may need a little bit more chemical testing, but at least they do leave literally embedded signs that we can track. A really fun one that a lot of folks don't know about is actually ice cores. All right, this is a great one. I love this one. This is the sort of piece of science that you wouldn't necessarily think was possible. I love that we can do this. Check this one out. Ironically, because of climate change, our ability to use this form of indirect evidence may be shrinking, may be going away, but ice cores are samples of air that was trapped in an ice flow, in a glacier or an ice sheet during prehistoric times. And they're literally samples of air that have been trapped in frozen ice so quickly that the contents of the air in these pockets is still completely sealed, airtight. And when we can find them, you can see when you're coming up on one, when you're moving through the ice, you can see the bubble coming up. And if you can, we can slowly drill into the bubble and get a gas probe with a meter attached down into the ice probe, and we can actually read the balance of different gases that were present in a prehistoric atmosphere. Because the air sample was frozen so quickly, and it's been airtight ever since and hasn't been accessed until scientists get in there with the gas meter, we can actually look at what are the balance of different gases in this sample of prehistoric atmosphere. And okay, fine. I'm a science geek. I love biology. I love pretty much any science I can study, but this is really fascinating. This is fantastic. It's a time capsule. It's a time capsule that tells us exactly what the atmosphere was like hundreds of thousands of years ago, maybe even a million years ago. It's fantastic. It's this wonderful, just sort of snapshot of atmospheric chemistry and atmospheric balance from long before. Usually when we can access these, they come from a period long before historical records were being kept, and they even come from areas where usually historical records weren't going to be possible because human habitation typically wasn't that huge in areas that were covered in ice flows. And it is indirect evidence, but the amount of detail that we get, the amount of direct information we get, because we're not looking at, oh, this is a sign of the presence of this gas laid down in the geological record. No, this is the actual balance of gas laid down at the time. It's like a gift for trying to understand what climate was like, because it will also show us what the balance was at that time of greenhouse gases. And we're going to look at that in just a moment when we start looking at trends. There's one more major form of indirect evidence I want to cover with you because its source is alive. Its source is living, or if we can find it in a fossilized version, it was from a living being at one time. And these are core samples from trees. Now, as a lot of you will already know, trees have growth rings coming out from the center of inside the tree out toward its bark. Some of these growth rings are more narrow and closer together. Some grow much broader apart with much wider bands. And what determines this is how much water they had access to in a year. Other things that affect this are the overall health of the tree. A tree that's suffering from a disease or some kind of parasite isn't going to grow as well, and that can curtail how much those growth rings would expand in one particular season. We can also see the effects of really powerful wind, because it'll change the direction the growth rings progress in the course of the grain of the wood. This is also why, say, if we have an individual that happened to have been sick during much of its lifetime or had beetles as a pathogen, this is also why we, as scientists, test more than one tree. And a core is not overly damaging to the tree as long as it's been done properly. It is very small. It doesn't have to be very large around. Most of them are no smaller around than your standard number 2 pencil. Sometimes they can be done even smaller. So they can be quite modest. It's not important that they be really big around. What is important is that they go all the way to the heartwood and back. The kind of information we can get from a sample like this is, most importantly for climate change, how much water was available during a given season of that tree's life. And we can count back from present growth rings and figure out roughly what season, roughly what year was that particular growth ring laid down when we want to figure something out about climate. If most of the rings look like they are the result of pretty decent access to water with really nice clear gaps in between the rings' perimeters, and then we get an area where suddenly things get much tighter, that's going to be a sign where there wasn't nearly as much water available. Here in Southern California, we know that kind of climatic event very well. We're still trying to get out from underneath the last drought we had, and that is a very clear sign of drought laid down not in a human-kept record, but as indirect evidence in the records kept in the growth rings of that tree or trees when we go sample them. So when we're looking at this indirect evidence, we're able to notice certain trends. We can learn things about how climate has changed over time for a region. So what are we learning? Well, we're learning that over time, there have been previous examples of gradual temperature change, even during human existence, but ones that, at least for the general public, we don't really discuss that often. For instance, during the medieval ages, what was the medieval ages in Europe? There was a sort of mini ice age from about 900 to 1300 CE in the Common Era. So for about 400 years, there was a break in the normal climate cycle for the planet, and there was a cooling period. And as you can see here, this is actually a temperature map for the planet during this period. Sorry, the warm period. We had a mini ice age as well later on. And you can see there are these larger pockets of overall warmer temperatures. And even though what we're looking at what we're looking at for measurement here, what you're seeing is a thermal map. Now, this is relative to what temperatures are like much more contemporarily. So overall, things look cooler compared to what the climate was like overall before this, before 900 to 1300 CE. This was a warm period. And if you've ever seen medieval art or sculpture, tapestry, you'll see throughout most of medieval Europe, clothing that, at least here in Southern California, we would probably associate with colder temperatures for us. For them, this was an overall warming period. So like heavier fabrics when they were available, long sleeves. wasn't just an expression of wealth, although it certainly was that too. It was an adjustment for climate. It was a lot cooler than we would associate with our modern era, especially here in Southern California. But for their time period, that was gradually becoming warmer and warmer over this 400-year period of time. We've also seen a little ice age, and yes, it is actually called the Little Ice Age. That's both its common and its academic name, which is kind of fun, that happened after the medieval warming period. So this is from about 1550 to 1850 CE, almost dovetailing right into the Industrial Revolution and the climate change that we've been seeing since then. So for this 300-year period of time, we had a comparatively much cooler temperature. And this is a really nice graph. You can actually see what I'm talking about when I'm saying, okay, those medieval temperatures, at least compared to what we're used to now here in Southern California, looked relatively cool. But see beforehand, during what we commonly still call the Dark Ages, from about 150 to 950, depending on where you were on the planet, it was considerably colder, this here is the average summer temperature of the sea. So summer sea surface temperature, say that 10 times fast, with or without caffeine, in degrees centigrade. All right, so this may look a little bit different, especially here in the US, we're used to Fahrenheit. But the overall average, if you see here, the average here is a difference of about 9 degrees. Sorry, and it's overall much cooler before that medieval warming period. That temperature dropped off again and then dropped even further compared to what we know as an average modern temperature right now. So that medieval warming period was a little bit cooler than we're used to right now, but fairly close to what we would be used to before and after, considerably cooler by a degree, even two. And I will say this again when I talk about how this affects living things. A degree or two difference may not sound like a lot. And when I discuss this with students, this is something that comes up a lot, actually. A degree or two doesn't always sound like it's a huge difference, but when we start applying this to its effects, what are the consequences of a whole planet whose average temperature has shifted by a degree or two? The effects that this has on living things and on day-to-day life is really very dramatic. A little bit worldwide goes a terribly long way. So what are we looking at now? All right. Right now, and this industrial revolution, this round of climate change is the climate change that is still affecting us right now. And what we know is that it is tightly associated both with the Industrial Revolution and the change in how much fossil fuels we have started consuming, but even predates the Industrial Revolution a little bit. And that's a slightly more recent research that it actually predates. We used to count it from about 1850. Now we count it from about 1750 instead. And it is tightly tied. This latest onset of major climate change is tightly tied to an onset of fossil fuel consumption that has very quickly, in relative time, ratcheted up to the point where it's affecting our global atmosphere. And those changes are, of course, affecting the entire planet. Now, there are natural cycles of climate change. And if you ever happen to run into a major devil's advocate for the topic of climate change, you may have this point made. And it is true. A phenomenon called a Milankovitch cycle is the source of much of very gradual natural climate change over time. It has to do with the overall tilt of the planet toward or away from the sun as we go through our orbit. And it takes a long period of time. Note that these measurements between different regions in a Milankovitch cycle are talking about 19 to 24,000 years during a course of precession, or between major sort of exaggerated extreme points in the cycle. We're talking about 100,000 years to 413,000 years. That's natural climate change cycle as our planet has known it historically. And again, this is the sort of information we have learned over time from indirect evidence, because a lot of this will predate a better ability for people to keep records. We've also seen some climate change can be brought about by volcanic eruptions. All this ash and smoke being thrown up into the sky can have a bit of effect, like a lot of our really heavy wildfires earlier this year. And it can actually cool an area for a while. This is called a haze cooling effect. The more ash and smoke gets thrown up into the atmosphere, the more it can sort of temporarily shield the surface of the planet from heat that we would otherwise receive from the sun, and help cool an area for a while. And the more severe the eruption, like Pompeii or Mount St. Helens, the more dramatic the effects and the longer they'll last. That's not, however, what we are seeing for the vast majority of the climate change that we can observe and study right now. We can study the effects of Milankovitch cycles and haze cooling over time from direct and indirect historical records. And we know from descriptions of those time periods and from the evidence that we can find that what we are experiencing now is not behaving in the same way. And this is something we really need to come to terms with. What we are experiencing right now is predominantly to the tune of at least 95% that we can prove scientifically and mathematically because of the greenhouse effect. The greenhouse effect is caused by an increase in greenhouse gases in our atmosphere. These are gases like nitrous oxide, carbon dioxide, methane, and CFCs. At least CFCs are slowly trickling off and easing off as a source of the greenhouse effect. The other three are still very, very powerfully present in our atmosphere. And we produce these often as side effects of agriculture and industry. What they do, the reason why they have some effect on the overall climate of our planet, is they basically form a sweater around the Earth. They fill much of the atmosphere between the Earth's surface and space, and they insulate the planet. So when sunlight, and with it solar heat, reaches our planet and helps warm the surface of the planet, it cannot dissipate very easily from the planet. Before the greenhouse effect, reflected light and reflected heat would have been able to, and was able to, leave the planet and dissipate away from the surface of the planet much more quickly. But this combination of gases is such an effective insulation that it keeps heat basically rebounding between the atmosphere and the surface of the planet. And the longer it stays and the more it permeates that area, the more that area warms. And that means that there's a nice, warm, snuggly blanket surrounding the planet. And there is no way for the planet to say, get its feet at least uncovered from the quilt. This is not necessary. It's like wearing a blanket during summer. It's just plain uncomfortable. And all of the effects of that discomfort are what we know as our major evidence of climate change. I know everyone now who's like, oh God, I can't sleep without at least having one foot or part of one leg uncovered, or I just overheat in the summer. Now you know what it's like. So what do we know about what is going on right now and why? And why is it that I'm saying that this climate change, this round, is so different? Well, no surprise to anybody, but scientists the whole world over have been studying what's going on for decades, trying to understand how quickly is this happening? Can we pin down exactly what we're doing that's making it happen? Can we conclusively determine that it is us? And if it is us, what exactly is like the main culprit? And we do have answers on this, and this can be difficult information for some folks that you may encounter to deal with and to confront because it's painful. Um, just one example of the research that has been going on climate change for decades is the Intergovernmental Panel on Climate Change, the IPCC from the UN. This is a collection of over 113 professional ecologists, climatologists, and environmentalists studying the Earth's atmosphere, the gas balance of that atmosphere, climate change in the form of ice melt, temperature change, every aspect we can identify. And we have been able to identify that easily better than 95% of all probability is that we have warmed our own planet, mostly by the massive change in how much fossil fuels we use and the concentration of greenhouse gases we produce. I'm sorry, I was over 113 countries, over 1,300 different professionals working together cooperatively on different aspects of this information, of this study over time. Just trying to cover this as thoroughly and as in many different ways as possible. What we have learned is humbling, it is shocking, it is a massive call to action. It is a moral, it's an ethical call to action because of how powerful this change is. For instance, when we look at greenhouse gases, take for instance carbon dioxide. We've got a table here from the IPCC. We measure gas concentration in an area, in a volume, in terms of parts per million. So how many parts per million particles of the gas mix in that volume are the particular gas that we're studying. And one of the really valuable pieces of information that the IPCC has uncovered over time is that in the last 150 years, so pretty much since well into that onset, that since 1570 climate change onset, mostly due to industrialization, the parts per million average for our atmosphere, just for carbon dioxide, have leapt from about 280 to over 400, about 414 parts per million in the last 150 years. And I know 150 years might sound like a lot, but this is average global measurements just for carbon dioxide, just in our atmosphere. That's a massive change. And that is a massive change that's come about lightning fast. Remember, change that we have seen before historically in climate change, in our climate, has taken tens of thousands, if not hundreds of thousands of years on average, with like two highly notable exceptions in the last 1,000 years and more, each one of which has lasted no more than maybe 400 years. We are looking at something that is very different when we deal with contemporary climate change. And we're looking at a lot of effects of it. And I want to, before I get into these, because I want to talk with you about what are these results and what should we predict to see in the future. Do we have any questions? Can we answer anything for anybody really quickly?
Nothing right now in the chat. Just a quick time check. It is 11:40 to give you the heads up. But yeah, no, nothing in the chat so far. It's going great. Thank you, Lauren.
Okay. I'm trying as much as possible to predict what sort of questions folks might have. So hopefully this overall talk will be useful for everybody. So, and I'm going to go through these briefly, but you need to be aware that this information is open and available to you. All of the information that has ever been compiled by the IPCC, as well as a host of other scientific studies on climate change, is publicly available. I promise, I have included nothing in this talk that I only have access to because I'm a career professional scientist. Everything that you can see here is openly available to you. So this is a conversation you can full stop be part of, and you should be. It's your planet too. So major evidence, in many cases gathered by the IPCC, are an overall global temperature rise since the late 19th century, so since like the late 1800s. Our global temperature has already leapt by 2 degrees Fahrenheit. So we were working in centigrade before. In centigrade, that's about 1.5 degrees. Remember when we were looking at that graph between the Dark Ages cooling period and the medieval warming period? That major temperature shift that then dropped it back down into an ice age was a couple degrees centigrade. And we're already looking at more than 1 degree centigrade between a comparative warming period and an ice age. And now we are warming again. We are warming already past where we were for the planet in that medieval warming period. So things are not just warmer than they were during a mini ice age, during the little ice age, in fact. Things are becoming warmer than we have ever seen them be on the planet in the last couple thousand years. And they have hit that point in less than 150 years, where previously that kind of temperature change to get to where we are right now took a much longer period of time, took a couple centuries or more. So things are happening quickly and the effects are much more dramatic. We're also seeing sea levels and temperatures rise. The surface open ocean temperature has already risen by over 0.5 degree Fahrenheit, that's about 1/3 of a degree centigrade, since 1969. That is easily within most people's lifetime who might see this particular webinar. So this is dramatic change going on during your lifetime. And if that doesn't sound like a big change, there are all kinds of endangered species living in our ocean that have a temperature tolerance of maybe 1 degree, maybe 2. And we're already through 0.6 of a degree centigrade. That doesn't leave them a lot of leeway before temperatures have shifted so much that they have to shift where they live or not survive. We are actively looking at that reality right now. We're seeing ice sheets shrinking. Ice sheets that normally persist over an Arctic summer or maybe don't even melt at all have been melting over time. Greenland alone, for example, has lost about 279 billion tons of ice sheet per year between 1993 and last year, 2019. That's 16 years. That's it. Like, this is lightning fast compared to the entire history of climate change and what its effects look like. Some of that can be so dramatic, we may be looking at decreased, in fact, we are looking at decreased sea ice around the Arctic. We're losing a lot of our glaciers. They're shrinking here. They're shrinking in Alaska. They're shrinking in Canada. They're shrinking the whole world over. This is Muir Glacier up in Alaska between August 1931 and August 2004. Just mid-August versus the end of August. And believe me, that's, a couple of weeks are not enough difference to cause this. It's over time how much we have lost. We have both the burden and the privilege of living during a time period where these effects are so dramatically evident. And now we have the ability not to stop it. As you can see, it is too late to stop or prevent anything. But we have both the ethical burden as conscientiously minded people who care about the status of our planet and our country and what that's going to be like going forward. We have that burden and we have that privilege then to take whatever actions are possible to do the research, to make the changes, to try and curtail this and moderate it as much as we can for future centuries and future generations. And I know we're coming short on when I would like to do another question check, but I want to go through with you. What are some more of these things that we're seeing? You may come across people who don't understand how dramatic these effects are. And this is what we're talking about. We're looking at overall decreased snow cover around the entire world. This is a measurement just by sheer amount of coverage for a particular time of year. Between 1975 and 1979, so you can compare, and then between 2015 and 2019. So this is up to date, as accurate and as recent as we can get access to the information for research about how this has changed. And this is just for our northern snow cover. And you can see how much this has changed. So blue areas are in snow. Brown areas are typically without. And you can see just how much this has shrunk off and changed in the exact same part of the planet from one 5-year period to another. All right, this is the kind of change we're seeing. Sometimes it can be hard to notice when this change happens because it can seem gradual, but when you see snapshots that let you compare it like this, suddenly it just becomes incontrovertible. You can't ignore that climate change is happening and how powerful its effects are. Goodness, living here in the United States, we definitely know that the amount of precipitation we've been getting and instances of severe weather have seriously been changing over recent history. We used to live in a time period where the Gulf of Mexico, facing up into states like Texas, Louisiana, Mississippi, would get storms and even occasionally get hurricanes, but not like they do now. Now it is multiple times a year, where it used to be, you know, a hurricane coming through like Ike was a major historical event. Now they'll have a couple, maybe even a few, every single year. And they're becoming more severe as well as hitting more often. And overall precipitation patterns are changing. Heck, how many times have we had lately conditions that ought to have given us an El Nino year here in Southern California, but those wind currents that should have brought us that rain have shifted because the overall temperature of the planet has shifted, and it's pushed air currents into new pathways. So we aren't getting the weather that we are accustomed to getting. Meanwhile, at the same time that we're accidentally not getting our rain when we would really, really like to get it during a drought, on the other side of the country, in recent years, at the same time of year, during the winter, New York keeps getting buried in record-breaking snowstorms and blizzards. Their weather patterns have shifted around as well. And sometimes this can be what causes a little bit of confusion about, well, we keep saying global warming, and we're trying to say climate change now a little bit more often because it can avoid this sort of accidental confusion. Because even though California, well, hi there, Southern Californians, you tell me about our summers. They keep getting longer and hotter than they've ever been before. But because weather patterns the whole world over keep shifting, as the global average temperature keeps rising, some areas start getting dumped on with snow when they didn't used to. It doesn't mean that the planet isn't warming. It means that the consequence of that planet warming for that particular area has pushed cold weather into a new pathway, and now New York keeps getting buried with snow, while we keep missing the rain that really would have been helpful during our last drought. What else keeps happening? Well, we also keep seeing that as we keep layering more greenhouse gases into their atmosphere, we also get pollution and greenhouse gas diffusion into the surface of our oceans, and this is causing ocean acidification. Now, what you're looking at here isn't just a trend of the surface pH of the ocean, both what is actually happening in various oceans around the world, the Arctic, the Southern Ocean, and ocean water at the tropics, but also what that pH would look like if it were not for the effect of greenhouse gases. The lower the pH, the more acidic it is. And it is easily acidic to the point where small forms of marine life, like this zooplankton here. Zooplankton are a variety, actually, it's a whole large group of species, but it's a variety of nearly microscopic animals and animal-like life forms. They form the basis of a lot of food chains. They're a highly nutritious, reliable form of food for a lot of marine life. But a lot of them are protected by exoskeletons and shells, like larger shellfish. The ocean is becoming, especially the surface of the ocean, has become acidified enough now that when exposed to that acid layer, that low pH, over a course of a month to a month and a half, as you can see here from this study, these shells start to break down. And that means that that whole food source is going to break down. And when you lose a major food source like that, the entire rest of the ecosystem will be damaged. It cannot be avoided. When this happens, species that can move where they live may leave. So animals may leave an area. Plants may die off and end up surviving better elsewhere. As you can see, this is just here for a lot of the contiguous United States. And this is just for a lot of really common tree species and how their populations have shifted around. Areas that used to see certain species, like in the 30-year period before 1990, there was a lot of maple, beech, and birch forest up around Maine and Rhode Island, and they have lost the vast majority of that. Those trees aren't surviving in that whole area of the US anymore because of climate change. Instead, other species are surviving better in that area, and they have spread to fill in the gap. Now we're getting a lot more oak pine and oak hickory. And that means that the habitats that were created by that forest type, we're losing those as well. That means that the wildlife that lived there will die out or leave and survive better elsewhere. But as this continues to change, so we've got a projected timeline here, and these are going to be the consequences that we project and predict to see if climate change continues in the way it has been, at the rate that it has been. We're going to lose some of these habitat types, and that means we're going to lose those wildlife populations. They may move, but we may also lose them permanently. They may die out. These are just some of the effects that we're looking at. We're also seeing overall extinction rates kicking up, most of them directly due to human activity, but also indirectly due to overall climate change. And I want to skip forward a few because I do still want to be able to take any questions if you have them. But remember, all of this information is absolutely available to you. In fact, this is directly from the IPCC, this major graph here. This shows worldwide effects as they are right now. And these will only become more severe as time goes on. As you can see, we've got effects due to drought here in Southern California, and that is definitely affecting our living ecosystems, our wildlife. And if nothing changes, if we do nothing, we will continue to see global temperatures rise. We'll continue to lose more and more snow cover. Weather patterns and severity will only continue to change. We'll just see more of the same. Here locally in Southern California, that means more heat, more drought. Heat and drought conspire to eventually push even our really tough, wonderful native plants to the limit. And that means that when we get more wildfires, they will be larger and more severe. Yes, like this year, like 2020, where we have been setting all the wrong new records for wildfire. 2020, our wildfire season here in Southern California has contained both the largest single wildfire complex up by Sacramento, and it's also burned the largest overall area of habitat, of property, at any time that we have record for. So we've got the most area burned and the largest single area burned due to one fire complex. It's also going to affect our agriculture because hotter and drier means fewer and smaller harvests. And overall, heat, aridity, and smoke from wildfires will definitely affect people's health. So what do we do about it? We are scientists, and it is not just enough to understand what is happening, but what can we do with it? Well, remember, we know what's causing this. The lion's share of the effects that we are seeing are compounded and caused over time by the greenhouse gases that are building up in our atmosphere, like methane, like carbon dioxide. Much of these are due to how we create and use energy and how we practice agriculture. We have options. Now, so far, none of them are perfect, but they have potential. We are human beings, and our brains are exquisite at making new tools and problem solving. It's where play and art and imagination come from in the human mind. What we need to do is apply that incredibly well-developed ability to the options that we have to make them feasible for everyone. Things like solar energy, things like perhaps biofuels. There is a push now to make electric vehicles more and more accessible here in California. And it's a good idea, but there's a lot of infrastructure that's going to have to change so that people can charge their cars as easily as they would fuel them up with gas. So there's a lot of change that we need to make possible. But we also need to shift our state of mind so that that change is permissible. Some folks don't like changing their habits, not even for an excellent cause of survival. That's why we need to have conversations like this, and why I'm so glad that you've joined me this morning to become more involved in this conversation that's been going on for decades and that we are not done having yet. The more we can confront what's happening and start pursuing what we can do about it, the more we might be able to save, the more changes we might be able to lessen over time. And perhaps one of the species that we will save from extinction is our own. Now, I know we are right down to the line, but are there any questions that I can answer for anyone?
There's nothing in the chat, but you guys are welcome to unmute yourselves and ask Lauren a question directly.
I know I've thrown a lot of concepts and information at everybody today. Is there anything I can help anyone with?
While we're waiting, I did have a question for you. Could you talk at all about what signs of climate change you've seen personally in your professional activities, in your professional career? I'm pretty sure this is a subject you could speak hours on, but I remember being in class with you and you had I forgot exactly what it was, but you had a pretty powerful, impactful statement about professionally seeing climate change occur.
Gladly. So for the record, I'm a biologist. I study a lot of areas of biology, but I'm particularly a field biologist. I study ecology and animal behavior, and through that I study damn near everything else. Mammalogy, ornithology, that would be the study of birds, and everything else that they interact with in their habitat. In the course of spending that much time out in the field, I have seen weather change. I have seen new patterns coming into an area. That drought that we were trying to get through was one of the worst droughts in California record. That's both indirect record and human kept records. I've also seen migration patterns change night versus day. One of the most common things that will kick off a migration, that cues a migratory species that it's time to be on the move now, is the change of temperature overall during a year. And it used to be taking students out into the field or going out to conduct field research myself. I could fairly well predict what manner and variety of migratory species I might see almost at any given time of year in my local habitat. It's a crapshoot now. There is so much that's different. So many species have become residents in an area that used to be just part of their migration. So many species aren't leaving their overwintering grounds or aren't leaving their summer grounds. And for some populations, their migration is breaking down entirely. Some are losing so much habitat due to climate change and due to spread of human activity that there's hardly any population left to go through with the migration. It is, well, it certainly keeps you on your toes as a field biologist, I will tell you that. But look, to be perfectly honest, and when I function as a scientist, I don't normally get to talk about my emotional attachment to the wildlife that I'm seeing, my local residents, and the migratory species that I come through and see, and study. But it is alarming to see such a massive change, including complete population breakdown, easily within the length of my personal career, and know that that will only continue if we do nothing. I have seen areas that used to have healthy mussel beds where there's hardly anything now in an intertidal area. I've seen areas of our national forests that used to have healthy pine and mixed conifer forest, and because of heat stress and drought due to climate change, even they are pressed to the limit of their endurance. These are dramatic changes that I can describe, but I wish for everyone to be able to go see these changes for yourself. As a scientist, I highly encourage you, don't just take my word for it. Go out and see it for yourself, or go see the data for yourself. If you have questions, believe me, there are scientists in your community and we are happy to help answer your questions. But if you've ever felt like any of this jives with what you have experienced, or if you've ever felt like information is being handed to you that's been given to you with a filter, go see the information, go see the data for yourself. You have the right to. Like I told you, there's nothing here I've referenced or used today that is not available to the public. You do absolutely have the option to go experience the impact of these changes for yourself. And while that is a bit of a soapbox, I do hope that's a suitable answer for your question.
I think everyone in the room loves your soapboxes, so thank you for getting on your soapbox.
It's like, goodness, I'm not sitting in a chair. Suddenly there's a soapbox here. What happened? I got a question.
All right. Well, if we don't have any more questions, thank you everyone for joining us today. Especially thank you, Lauren, for giving us your information and your insight, and above all, your passion. It's always amazing hearing you speak. So we are going to be doing a number of these webinars, these live events, as well as doing a few recorded events. So we will keep everyone posted on what we are doing for the future. Please feel free to reach out to myself and to Luis at Dominguez Rancho Adobe Museum, as well as Mercedes and a few other of the interns and employees. If you have any more questions, yes, again, thank you all. Thank you, Lauren, and we look forward to seeing you guys soon.
It's my pleasure. Have a wonderful day, everyone, and thank you for joining us.
Thank you. Bye.